So what's a colloid engine?
So the same rocket people that came up with these ideas for electric propulsion, probably in the middle of last century, also realized that there's one more place to get charged particles from if you're going to be using electric propulsion. So you can take a gas and you can ionize it. But there are also some liquids, particularly ionic liquids, which is what we use, that you also can use as a source of ions. And if you have ions and you put them in a field, you generate a force. So they recognize that. But part of being able to leverage that technique is being able to kind of manipulate those liquids on a scale of nanometers or very few microns. So, the diameter of a human hair or something like that. And in the 50s, there was no way to do that. So they wrote about it in some books, and then it kind of died for a little bit. And then with silicon MEMS, computer processors, and when foundry started becoming more ubiquitous, and my advisor started at MIT, kind of put those ideas back together and was like, hey, actually, there's now a way to build this and bring this other technique to life. And so the way that you actually get the ions out of those liquids is you put the liquid in a strong electric field, and the electric field stresses the liquid, and you keep increasing the field, and eventually the liquid will assume a conical shape. It's when the electric field pressure that's pulling on it exactly balances the liquid's own restoring force, which is its surface tension.
Mm-hmm. Cool.
So you have this balance, and the liquid assumes a cone when it's perfectly balanced like that. And at the tip of a cone, the radius of curvature goes to 0 right at the tip, and the electric field right at the tip of a sharp object would go to infinity because it goes as 1 over the radius and 1 over the radius squared. And instead of the electric field going to infinity and maybe like generating a wormhole or something, a jet of ions instead starts issuing from the tip of that liquid. So the field becomes strong enough there that you can pull ions out of the liquid.
What is the liquid we're talking about? Or is it there's a bunch of different ones?
You can do it with different types of liquids. It depends on how easily you can free ions from their neighbors, and if it has enough surface tension so that you can build up a high enough electric field. But what we use are called ionic liquids, and they're really just positive. They're very similar to salts, but they happen to be liquid over a really wide range of temperatures.
This sounds like really cool. Okay, yes. So how big is the cone we're talking? What's the size of this cone that generates the ions? So
if you have a cone that's emitting pure ions, I can't remember if it's the radius or diameter, but that emission is happening of that cone is something like 20 nanometers.
Oh. I was imagining something slightly bigger, but this is tiny.
Yes.
Hence the only being able to do it recently.
Yeah, that's right.
So this is all controlled by a computer, I guess. How do you control? How do you create a cone that generates ions at a scale of nanometers exactly?
So the kind of main trick to making this work is that physically we manufacture hundreds or thousands of sharp structures and then supply the liquid to the tips. So that does a few things. It makes sure that we know where the ion beams are forming, so we can put holes in the grid above them to let them actually leave instead of hitting, right?
Cool.
But it also reduces the actual field the voltage we have to apply to create that field, because the field will be much stronger if we can already give the liquid a tip to form on. And those tips we form have radii of curvature on the order of probably like single microns. So we are working at a little bit larger scale, but once we create that support and the electric field can be focused at that tip, then the tiny little cone can form on top of that.
So there's something there's an already like a hard material that like gives you the base for the cone, and then you're pouring like liquid over it, whatever.
From the bottom, it's porous, so we actually supply it from the back of the chip, and then
liquid
wicks.
Forms on top, on that structure.
Yeah,
and then you somehow make it like super sharp, the liquid, so the ions can leave.
And then we've applied that field to get those ions, and that same field then accelerates them.
That's awesome. And there's like a bunch of these.
Yeah, I should have brought something. So
you could just pretend that you have some nanometer cones on the table.
So actually, kind of about this scale, we call them thruster chips, and it's just a convenient form factor, and it's a square centimeter. And on each square centimeter today, we have about 500 of the actual physical, we call them emitters, those physical cones. And we're working on increasing that by a factor of 4 in the coming months.
In size or in the density?
In the density, the number of emitters within the same square centimeter chip.
So that thing, because I think I've seen pictures of you with like a tiny thing in your hand. That must be the thing. Okay, so that's an engine.
So that is kind of the ionization chamber and thrust producing part of it. What's not shown in that picture, is the propellant tank. So we can keep supplying more and more of the liquid to those emission sites. And then we also provide a power electronic system that talks to the spacecraft and turns our device on and off.
So that's the colloid engine.
Yeah.
That's the core of the colloid engine.
It's the way I've been talking about it. It's more of ion electrospray. Colloid tends to mean like liquid droplets coming off of the jet. But if you make smaller and smaller cones, you get pure ions. So we're kind of like a subset of colloid, yes.
What aspects of this, you said that it's been full of mystery from the physics perspective. What aspects of this are understood and what are still full of mystery?
Yeah, recently we've been understanding the kind of instabilities and stable regimes of, how much liquid do you supply and what field do you apply and why is it flickering on and off, or why does it have these weird behaviors? So that's in the past just couple years that's become much more understood. I think the two areas that come to mind as far as not as well understood are the boundary between, you have, we actually use kind of big molecular ions. And if you're looking at the molecular scale, you have, some ions that you've extracted and they're in this electric field. One ion, it's a big molecule. It's getting energy from the electric field, and some of that energy is going into the bonds and making it vibrate and doing weird things to it. Sometimes it breaks them apart. And then zooming out to the whole beam, the beam has some behaviors as this beam of ions, and there's a big gap between what are those, how do you connect those, and how do we understand that better so that we can understand the beam performance of the engine.
Is that a theory question or is that an engineering question?
Theory, definitely. Axion is a startup, and we're more in the business of building and testing and observing and characterizing, and we're not really diving much into that theory right now.